Hey guys, I'm Niharika and welcome to today's session on InsertionSort. By the end of this video, you will understand exactly how this algorithm works, how to code it, and when to use it. Before we start, here's a quick map of what we will be covering today. We'll begin with a short introduction, then talk about what InsertionSort actually is, and then I'll walk you through its working with step-by-step visuals, followed by the code implementation. Next, we'll look at the time and space complexity and finally wrap up things with a few key takeaways. So let's get started. So what exactly is insertion sort? It's a comparison-based sorting algorithm, meaning it works by comparing elements and arranging them in order. The idea is simple. We start with an imaginary sorted portion on the left. Like here you can see below an array in which you can see the green boxes which are the sorted part of that array and the red boxes which are the unsorted part of that array, and the gray box, it is where the pointer is pointing for comparison, and we'll see more about these things in the working section. It's efficient for small or nearly sorted lists but not ideal for large datasets, and you will also see the reason in the coming sections. So let's discuss the working of this algorithm now. So firstly we will take an array or a queue or anything you can consider as a list. So as you can see, this one here that I have taken is an unsorted array. 5 2 9 1 5 6, they are unsorted and in no order. So firstly we will take one element, like we have to take the first element 5, which is from the left. We will go from left to right in this tutorial. We consider the first element left since it's the only element in the sorted part, so it will just directly, we will just directly save it to the sorted part, and as you can see it has gone green. So in now we have the green part, that is the sorted part of our array, and the red part which is the unsorted part of our array, which we have not explored yet. So now we will go to the second part, which is the 2 here. So what we are going to do is we are going to compare the 2 with the sorted part of the array, each element step by step. So here you can see we only have one element, which is 5, which is at index 0. Okay, so how will we compare it? So what we will do is we will take a temporary variable named temp, and we will store the value of 2 in the temporary variable temporarily. So what we will do is we will take a temporary variable named temp and we'll store the value of 2 here temporarily. So now we will compare the value of 2 with all the elements in the sorted part of the array step by step. So like we will move from right to left in the sorted part. So we here can see we only have 5 here in the sorted part, so we will compare 2 with 5, and as you can see that 5 is greater than 2. So what will happen is 5 will move to the right. Here we can see 5 has moved into the right, and then we don't have anything else to compare, so 2 will move here. Okay, so now we have two elements in the sorted part of the array, as you can see 2 and 5, and these things we have not explored yet. So we will move forward. Here you can see the third element 9. So comparing, we are again going to compare 9. As you can see we have stored it in the temporary variable. Now when we compare 9 with 5, because we have to go from right to left in the sorted part, so we are going to compare the 9 with 5. So 9 is greater than 5, so nothing will happen and the 9 will go to here, and then we will have this part as the sorted part, and this part we have not explored yet. Now we will move forward. We have 1 here, so we will store it in the temporary variable. Now we will step by step compare it from right to left in the sorted part. Like when we compare 1 to 9, 1 is less than 9, so the 9 will move here. And then we will compare 1 to 5, 5 will move here. We'll compare 1 to 2, and the 2 will move here too, and then we have nothing here, so 1 will move here. And then this is here, we have the sorted part. Now we'll move forward. The fifth element, that is 5 here, so we will just store it in the temporary variable. We will
start comparing it from right to left in the sorted part. 5 is less than 9, so 9 will move here, as you can see here. And then 5 is not less than 5 है ना, so 5 will move here, not here, as you can see this. And we will see this part as the sorted part. So now we will see the sixth element, that is 6, and similarly we will get it in the temporary variable, and then we will start comparing it with 9. As you can see, 9 has moved in here because 6 is less than 9, and then 6 will go there. And in this way we have sorted our array with insertion sort algorithm, and this is our final sorted array 1 2 5 5 6 9. Now I will show you the code in Java language.
So now I'm going to discuss the code for insertion sort. So firstly, I assume you have the basic knowledge of Java programming language, like the uses of methods and arrays, etc. Not the advanced knowledge, but the basic one. So here, let me explain the main method for you. It contains the array with the data type int. It contains 5 to 9156, which is a predefined unsorted array. Okay, and then I'm printing out the original array string, and then I'm printing out the original array by using the print array method. What this print array method is doing is it's using a for loop to print the elements of that array one by one, and we are passing the array as a parameter here. And then we are using the insertion sort algorithm, which is again a method inside the main class, by passing the parameter array in here, and then I'm printing out the sorted array by again using the print array function. So now in this section we will be writing the code inside the insertion sort method line by line. So firstly, I'm going to make a variable named n, which will be storing the length of the array here. Like this one is array, so I'm using this arr dot length. Okay, so now I'm going to traverse through this array using the for loop for int I is equals to 1. So you can see I am not using 0 here. Like basically when you traverse through an array, you take 0 here, as the 5, which is the starting point of this array, has the index value 0, but I'm using 1 here. So you can say I'm starting with 2, assuming that 5 is itself a sorted part of this array by default. Then I'm traversing I less than n, and then I plus plus. So now inside this for loop, what I'm going to do is, like I have discussed before, I'm taking a temp variable which will be storing the value of 2 here. So it will be storing the value of arr I. Okay, and I'm also going to take a variable j, which will be I minus 1. So where this j will point is, it will point to the rightmost element of the sorted array. It's pointing 5 at 5 here. Like assume if I is here, then j is here. Okay, so now what I'm going to do is I'm going to um, like this 2 has disappeared from here and it's here. है ना? So what we will do is we will start comparing this 2 with 5. So I'm again using a while loop, and the conditions for this while loop is j must be greater than equal to 0. Like j must not be less than 0, otherwise it will give null pointer exception. And for the condition we will use arrj must be greater than the temp variable. And so what will happen is the 5, when compared to 2, it's greater than 2, so it will move to the right. So let me move it to the right. Arr j plus 1. J plus 1 here is second index, and it will contain the value of arr j, and we will decrease the value of j one time. So we will move the j to minus 1, and when it fails the condition, it will just come out of the while loop. And now what I'm going to do is, when the 5 has moved from here to here, I'm going to place this 2 here. How I'm going to do is ARR j plus 1. As the j was here at -1, we have to move the j here at 0. Okay, so I'm using j plus 1, which will be equal to temp. So now let's try running this code. As you can see, we have the original array here and we have the sorted array here. So it's working perfectly.
Okay, so as we have covered the code in Java now, we are moving forward to the time complexity. So in time complexity, we have three cases here: best case, average case, and worst case. So what are these cases? The best case occurs when the input array is already sorted, like when 1, 2, 5, 5, 6, 9 are already in order. So what will happen is, as the array is already sorted, the pointer will move from one point to another and it will just cover the array one time. So whatever the length of the array is, it will cover only that length, so the time complexity will be on. In the average case, this order will be random. Okay, it's not strictly ascending or strictly reversed, so anything can happen. So in this case, we are taking the time complexity as on square. And in the worst case, the order will be strictly in reverse, like 9, 6, 5, 5, 2, 1. So what will happen is, the pointer will come here, he will see 9 here, and he will store it 9 here, because this is the only part of the array right now, of the sorted array right now. So when it will move to the next part, it will see 6 here, and the 6 will be shifted before 9. Similarly, the 5 will be shifted before, the this will be shifted before, this will be shifted before, and in this way the time will be taken n square time. In this way, more time will be taken and the time complexity will go to on square. You can also understand this with the graph here. As you can see, the unsorted part, which is the green part, is taking less time from sorted in descending order, and more time from sorted in ascending order. Sorted in ascending order is the best case scenario here, and it's taking 0 runtime in second, and the sorted in descending order, which is the reverse part, is taking much more runtime than both of these. Now the space complexity. The algorithm is in place here, meaning it sorts the array within the same memory. Like, as you can see here, it takes one temporary variable and all other memory is itself the array. No extra memory is taken here. Okay, so therefore the additional auxiliary space complexity is O1, constant extra space. So now we have come to the final thoughts about the insertion sort algorithm. Firstly, this algorithm is simple and easy to implement. Like, insertion sort is straightforward, it's easy to understand, and it requires a minimal code. Efficient for small or nearly sorted data, as you have already seen that it's efficient for small data, but it's inefficient for large data set. High overhead for shifting. The algorithm requires frequent shifting of elements, making it less efficient for large or unordered data set. As we have already discussed, with the large data sets, we have to perform shifting a lot of time, and this makes the algorithm less efficient. Small or nearly sorted data sets. So where is this algorithm actually used? So the answer is, it's used for small or nearly sorted data sets. As you have already know that it takes like O1 space complexity and On time complexity for nearly sorted data sets, so it's very efficient for those data sets. For real-time systems, suitable for scenarios that require low overhead and adaptive performance on small data, and use it when performance on large dataset is not a critical factor. So when we do not have a large dataset, we have a small or nearly sorted dataset, then it's better to use it in that situation. So that's all for this video. Hope you have understood insertion sort. Thank you.